Hello friends, welcome to this new video on stiffness reduction factor. This is some reference with our previous video number EQ11 where we have discussed the stiffness reduction factor to some extent. So this is a continuation of that, and we shall see other literature, what are the values given for the stiffness reduction factor. For your information, this stiffness reduction factor is also known as stiffness modifier. So this value of stiffness reduction factor is actually, which we have seen in the last video, actual stiffness by gross stiffness, and actual stiffness is also known as effective stiffness. So it is effective stiffness by gross stiffness, and in symbolic form you can write R equal to EI effective divided by EI G. Ig is the gross moment of inertia, E is the modulus of elasticity of the material. But from moment curvature relationship, m by EI equal to phi, m by EI equal to phi, the curvature. So from this relationship we can write EI effective equal to my by phi y. This EI effective is actually for any moment it is valid m by phi at a particular point instant. At yield point we have considered the situation, so there it is EI effective equal to my divided by phi y. My is the yield moment and phi y is the yield curvature of the material. So substituting this value here, finally we get the stiffness modifier or stiffness reduction factor is given by my divided by phi y, whole thing divided by EIG. Now let us see how to implement this, what are the values given for value R in different literature. I is equal to BD cube by 12, Ig, the gross moment of inertia. For concrete section, let us see what is the stiffness modifier. Concrete section may be cracked section, meaning tension develops at one part of the section. So due to fracture action, there will be a neutral axis. Above the neutral axis there will be compression, and below the neutral axis there will be tension. So here we have taken a beam section. Here is the neutral axis. Based on the amount of steel, FCK, FY, etc., the location of the neutral axis can be ascertained as per design mechanics. Now below the neutral axis tension is there and concrete cannot take any tension. So this part of the concrete is ineffective in imparting the moment of inertia. So we have a section something like this which is valid only above the neutral axis in the compression zone. And in the tension zone, since concrete is weak in tension, its contribution to moment of inertia cannot be considered. So it is disregarded. In a column section it can be slightly different, because in the column section the moment can be eccentric about both the axes. When moment is eccentric about both the axes, the neutral axis may be inclined like this as shown here. So area above this will be under compression, this hedged portion is under compression, and below this under tension. So this part is to be neglected. So this part is not contributing anything to the moment of inertia or rigidity of the section. So as such, because of the presence of tension in the concrete section, there is the question of the stiffness modifier or stiffness reduction factor which comes into picture. That is what is written at the bottom. So why do you need a stiffness reduction factor or stiffness modifier? Firstly, entire section is not effective in giving moment of inertia, just we have seen. The stiffness reduction factor or stiffness modifier to be used for this purpose. As seismic load is dynamic in nature, that is changing with time, neutral axis also will be changing. So all the time if it is changing, I cannot use the stiffness reduction factor which is changing. It will be difficult. In design it is not possible to use the change of the stiffness reduction factor step to step. So what we can do, we can take some average value of this stiffness reduction factor and use in design. So these empirical constant values of stiffness reduction factors have been suggested in literature that we shall study. First we have considered the stiffness reduction factor given in FEMA 356 in the year 2000, FEMA stands for Federal Emergency Management Agency. They produce documents for earthquake, floods, and all other hazards and give a corresponding number. So this way the document name goes. So it is given for different components. Beams non-pre-stressed, flexural rigidity is 0.5 ECIG. EC means the modulus of elasticity of the concrete. And IG is the moment of inertia of the gross section. For beams which are pre-stressed, it is ECIG. Now see why the difference is coming. When it is pre-stressed, it is under full compression. In compression, tension does not develop. So there is no question of reduction in the area. So full section is coming into picture in the rigidity EICIG. Columns with compression greater than some value is given by 0.5 AGFC dash, the concrete strength. The rigidity, flexural rigidity is 0.7 ECIG. The documents are giving the values of flexural rigidity, and we started with stiffness reduction factors. So these coefficients given here are the reduction factors, 0.5, 1, 0.7 and like that. So when compression is large in the column, less tension will be developed, so we allow 0.7 ECIG as the rigidity, and when the compression in the concrete is less, given by this expression 0.3 AGFC, then it is less. The flexural rigidity is only 0.5 ECIG. Walls when uncracked, cracked or uncracked here is not meaning the first term that we have used in the first slide, tension. It is not. Here it is on inspection. So please note this, that here the FEMA is referring to the actual damage in the wall. If it is uncracked, no damage, then the flexural rigidity is 0.8 ECIG. If the wall is cracked or damaged, then it is 0.5 ECIG. This confusion between this actual crack and the tension crack, or that we call as the crack section, that we shall be discussing in the next slide, some slide. For shear rigidity, it is constant for all cases, 0.4 EC AW. AW is the wave area of the section. Axial rigidity is no reduction, EC AG. AG is the axial rigidity. Is AE or EA is coming into picture. So it is full thing is considered, because axial rigidity, axial force is compressive force. Axial force is compressive force, no tension, so no reduction here. So note that here that crack section, as per the nomenclature of concrete crack section, indicating absence or presence of tension, is reflected here. But actual crack or damage is reflected in the case of shear wall as given here. Now let us see what our IS 1893-2016 is telling regarding this. For Artian masonry structures, 70% of the I gross of the columns and 35% of the I gross of beams. So stiffness reduction factor for columns is 0.7, and that for beam is 0.35 in IS code. For steel structures, I gross of both beams and columns are used. So here steel can take tension in both both the sides. That is, it can take the stress in the compression as well as in tension. So if so, there will be no reduction due to the presence of tension, and so we are using full gross moment of inertia in calculating the rigidity term, or in other words, the stiffness reduction factor is 1.0. Now we are taking the SCI 4117, which was published in 2017. Beams non-pre-stressed 0.3 ECIG. It is less than what was in the previous case of FEMA 356. It is less because it has been updated. FEMA 356 was in 2000 and it is 17 years newer. So this reduction is there based on experience. Beam when pre-stressed, it is fully under compression, no tension, so no reduction, ECIG. Columns with compression of certain level, there is more compressive stress is there, 0.7, and columns with compression when it is less, then tensile stress will develop, so it is now 0.3 only. For walls cracked 0.35. Walls uncracked is not given here. So walls cracked 0.35. And shear is same as earlier, 0.4 everywhere in all kinds of elements. And axial is also 1.0, stiffness reduction factor, ECIG. ECE is given in some cases, indicating it is the expected modulus of elasticity. Now let us compare these all three documents that we have visited in a single slide so that we can compare. So we are putting the items, then FEMA 356, SC 4117 and IS 1893 2016. So non-prestigious beams and prestigious beams are given as 0.5 and 1 stiffness reduction factor. For ASC it is less. In FEMA it was more. With experience it was noticed it should be considered less. So it has been taken 0.3. And when it is prestigious 1.0. 1893 it has taken some average value like 0.35 ECIG, and it has not made any distinction between non-prestigious and prestigious beams. Now for columns, column with large axial stress, the values are 0.7, both in FEMA 356 and in ASC/ACI 4117. In Indian code also it is 0.7. When column with small axial stress, small and large, we have discussed in the last slide, certain axial stress ratio is given. Based on that, if it is small, then it is 0.5 ECIG. Small means there will be development of tension, so it is less. And ASC/ACI has given still smaller, 0.3 ECIG. Indian code has not distinguished between small and large, and the stress level is disregarded here, and the average value is given 0.7 ECIG. For shear wall, physically cracked, it is not tension cracked. Physical crack, physical damage 0.5, no damage 0.8. As per ASC, it is 0.35. Now, for axial rigidity, it is always ECIG, no reduction. For shear rigidity, it is for all documents, for all cases 0.4 ECAW. Because we want to avoid shear failure. In shear, if it fails, it will fail in brittle nature. Suddenly it will fail, and we shall not get any energy dissipation through hysteresis in shear failure. So, shear, we have taken more factor of safety. In other words, we have reduced the available resistance in shear or rigidity in shear, ECAW, only 40% taken. Steel structure, as I said, it is equally good in compression and tension. So, the no reduction is there and the value is 1.0. That's why the rigidity term is ECIG. Stiffness reduction factor is also called stiffness modifier. How to assign the modifiers to the members in a model? So for that purpose, we shall take a SEP 2000 model and show how to apply these modifiers in a particular members. To see how the modifiers can be applied on the members, let us consider a building model in SEP 2000 software. So you can go to the define and then go to the section properties, then frame sections, and select say beam. So we select this beam and go to the modify show property. Under this, you are seeing the section of the beam. And there are two axes given, axis 2 vertical and axis 3 horizontal. These axes will be required in our understanding of the modifiers. Then click the set modifier option here and you get a dialog box where all the modifiers can be given. For example, here cross-sectional area modifier, it is default one. If you want, you can change it to 0.7 say for certain case of axial rigidity. Then shear area in 2 directions, shear in 3 directions, torsion constant, moment of inertia about 2 axes. So what is 2 we have seen in the background, 2 direction. So moment of inertia in the 2 axes may be say 0.35. You can give it. Similarly in the other direction, 3 direction also, say it is 0.35. And give OK. So these modifiers will be embedded with the beam section whatever we have chosen. So this way we give all the modifiers or the stiffness reduction factors in the members before we go for analysis or design. So phi y we have obtained the relationships. Now let us see how to get the value of my, the yield moment. Now for your information, the yield moment cannot be obtained from any mechanics. No design mechanics will give you the value of my, the yield moment. It is obtained by bilinearization of the force deformation behavior, generally the moment curvature behavior. So then also it will be very difficult for first drawing the moment curvature diagram, then bilinearizing it by the standard method. But in SAP 2000 like software, the value of MY is available in the hinge properties. That we shall see now. To get the value of MY for any section, how to get it from the SAP 2000 software model, let us see. So let us go to define, then section properties, then we go to hinge properties. So a dialog box comes like this. Here you have to click this show hinges, then it will start another dialog box and show generated properties. You click this, so it shows all the generated properties. Any hinge are given by a number here, you can select, and this is M3 means is a moment hinge. So if you click this, then you can go to show, modify show property dialog box here, and come here, modify show properties. So this is the hinge property. This is the force deformation behavior as per FEMA documents or ASC document, whatever the software is using. And in this you have the yield moment available here. So this scale factor and the moment you are seeing here 348 point something. It is in the gray color, so not so nicely visible. Anyway, the value is 348 kilonewton meter, because my unit here is kilonewton meter. So this is the yield moment. So this way you can get yield moment for any element, beam or column, whatever. Now there is confusion about the crack section, as I have mentioned again and again in different cases. Crack section actually mean by terminology a concrete section with tension on one side, that is below the neutral axis. So this is the theoretical or established crack section. But when a structure is damaged, it is also called crack section. So in that case, actual crack is there under external actions. Now the documents we have discussed, they have given empirical modifiers, not based on strength. In our video number EQ11, we have discussed a lot of things about the stiffness and its changes. So the empirical modifiers given here in the documents in this current video are partly for tension and partly for actual cracks, because we have seen for shear wall, FEMA 356 was talking about actual damage. In undamaged condition one value, in damaged condition another value. Otherwise they are all talking about this first one, crack section, meaning having some tension below the neutral axis. This is established by the fact that for steel structure no reduction is there. So it is not actual damage. In steel structure also under earthquake there will be actual damages. There will be damages in members. So in that case tension also will be developed there. But in steel structure the tension side and compression side both are equally strong. So the stiffness reduction factor is 1.0 or there is no reduction. So the confusion about the crack section, finally we can say that actual meaning is this crack section is where tension is developed, and because of that all the documents are giving stiffness reduction factors. Now this, if there is a confusion how to avoid it, this can be avoided by this process. Controversy may be avoided by using stiffness reduction factor or stiffness modifier by considering actual design strength. So based on strength we have seen how the stiffness changes. Stiffness changes directly in proportional to the strength. So if you use this, you are using the actual modifier actual theoretically established modifier, and there will be no question on this. So this formula also we have seen in the last video. The reduction factor equal to yield moment divided by yield curvature, whole thing. Thank you very much for watching the video. Please subscribe the channel, like and share the videos. Put your queries, technical queries in the comment box. I shall be glad to answer those queries to the best of my knowledge. Thank you and see you again in the next video.